Hey everyone, welcome to the first video for section 2.6 in the textbook, where we're talking about exact equations. So exact equations are another type of first order ODE, another sort of classification you can put on them that also has a fairly easy way of finding a solution. So in this section we're going to go into sort of what they are, how we solve them, and then sort of deal with some other properties and stuff they have from there. So in this first video we're going to talk about what they are and how you can identify if an equation is exact, which is the important first step for figuring out how to solve them. Let's go ahead and jump on into that. So the first question to ask really are, what are exact equations? Well, we're going to start with our most generic form of a first order ODE, where we have some function m of x, y, plus a function n of x, y, times dy dx equals 0. We showed in the first part that you can write the function where you have dy dx equals f of x and y. You can write in this form fairly easily. Now, we say an equation is exact, so this equation here is exact if there exists a function psi of x, y, so that it's going to have to meet three different conditions. So we're defining the word exact. This equation here is exact if, 1, the partial derivative in the x direction is m, 2, the partial derivative in the y direction is n, and 3, this expression equal to a constant implicitly defines y as a function of x. So what does this last one mean? This last one means that it's not just like a vertical line, right? It means that at least nearby points that we care about, this defines y as a function of x. Really all we care about is that it's not vertical. So if there's a function c that satisfies these three conditions, we call this equation 1 up here. We say that that ODE is exact if there is a function psi such that these three things are satisfied. The x partial is m, the y partial is n, and if you write psi of x y equals a constant, that implicitly defines y as a function of x. Now, if I have something like this, then finding a solution is fairly easy. Well, why is that? So my equation is mxy plus n of xy dy dx equals 0. If I have this function psi, I can plug what I know in, and I know that that means that I have here psi x of x, y plus psi y of x, y dy dx equals 0. Right? If I just plug in m is psi x and n is psi y, that's what I get. But now what is this? Well, if we go back to Calc 3 and look at what the chain rule is, since I'm defining y as a function of x, let me write that more explicitly, and then we'll write this out again. So psi x of x, y of x, plus psi y of x, y of x, dy dx equals 0. This is just, if we go back to Calc 3 and the chain rule for Calc 3, this is just the total derivative in x of psi of x, y of x equals 0. Because what happens when I take the derivative? I take the derivative, I do partial psi partial x, and then dx dx. X is what lives in the first component, and that's just 1. Plus partial psi partial y times the derivative in the with respect to x of the y component, which is dy dx. So I get this equation right here, and we know the answer to this because if its derivative is 0, that means it's a constant. So psi of x, y equals c gives integral curves for the ODE. And how do you find c? You find c from the initial condition. The initial condition tells you which of these integral curves you're going to live on, and then so that just picks out your curve for you. So a quick example of this. If you look at the equation, 4x plus 6xy plus 3x squared dy dx equals 0, I can take the function psi of x and y to be 2x squared plus 3x squared y. Now, if you look at this, if you take the x derivative, you will get 4x plus 6xy. If you take the y derivative, you will get 3x squared. So this psi meets our conditions, and it's a nice enough function that locally it will define y as a function of x. So the integral curves are of the form 2x squared plus 3x squared y equals a constant. So there we go. If we know an equation is exact, then that's really easy to do. But now the question becomes, how do we actually determine if an equation is exact? How do we determine if such a psi exists? So determining if psi exists. Well, I know if I have m equals psi x and n equals psi y, well, Calc 3 tells me I can switch the order of differentiation. So I know that I need to have psi xy equals psi yx from Calc 3. But psi yx is just n sub x, the partial derivative of n with respect to x, and psi xy is just m sub y, the partial derivative of m in the y direction. So these two must be equal if the function psi is to exist. And it actually turns out that since we're in two dimensions, this is actually both necessary and sufficient. So if this is satisfied, then my equation is exact. So now I'm going to write up theorem 2.6.1, which is exactly the statement here. All right, so there is the theorem. It basically says that if all my functions are continuous, which we're going to pretty much assume they are, then my ODE is exact and can be solved in the way we discussed above, if and only if the partial derivative of n with respect to y equals the partial derivative of n with respect to x. So all we have to check is take the y derivative of the m function, the x derivative of the n function, and make sure they're equal. If they're equal, it's exact. If they aren't, then it's not. It's if and only if, so that's what we get out of that. So this actually being sufficient is similar to the idea of conservative vector fields from Calc 3, but that's kind of a side note. So we'll see in the next video how we actually construct these functions psi from this condition here. But for now, I'm going to give you a couple problems that we're just checking to see if an equation is exact, which is just, again, you want to check this condition here and then you're good. So I'll put those problems up and then we'll move on in the next video. All right, so here's your problem for this video. Write that on the worksheet and do it from there. You're just checking to see if the equations are exact. I don't need you to find the function psi if it is. I just need you to see, is it exact? Use the condition we discussed before and check that. All right, thanks a lot for watching. And in the next video, we'll go about how we use these, why this method works, and go through how we actually find this function psi to do this exactness method. All right, thanks for watching, and I'll see you in the next one.